we had a very interesting discussion, partly because I started out with a meta question to the group with respect to scalability, and it holds also true for complementarity, and that is whether it's even premature to start talking about scalability of formal methods for AI systems for robustness when we are still laying the foundations of the techniques, the properties, formalizing what needs to be done, even asking what properties do we want to specify and what properties do we want to verify. So there was some general agreement, I believe, that we are anxious, but we do need to lay the foundations. And so scalability should always be in our minds when we are inventing techniques, but it's okay if things do not quite scale yet, because first we need to invent the new techniques and ensure the techniques actually do something useful. And I would say we didn't have as much of a conversation on complementarity, but I think there was general agreement that, again, for that, we need to take some perspective on the fact that we're embarking on what I would say a new research agenda. Back to scalability, some things that we echoed was, again, what properties do we actually want to verify, and the issue of, the specifying what I'm calling the data D or the environment, even knowing what the model is, what we can assert is provably true with respect to the data is something that we're still grappling with. If it's a given data set, then we know what we can do, but obviously we want these models to work on unseen data, and so that's where things get challenging. For sure, the techniques that people are already inventing are working and showing promise, and I think the individual presenters know how they would want to scale their techniques and also how to integrate their techniques with others or integrate other techniques with theirs. And we had some very good examples because we had Mark Muller there talking about his own fairly compositional, architecture that already integrates different techniques. And so I think what the bottom line is, we were very optimistic, but we're also reminded, and that was mainly me, the old timer, reminding us that formal methods for regular computing systems, got off the ground 40 years ago. And so we do need to remember to have patience. And most importantly, I would like to argue is laying the foundations so that we can build on methods and tools with in mind of scalability and complementarity is the important thing to do now.
Okay, so in our group, we started with discussing the scalability issue, and especially for those computer vision models, we feel it's really hard to apply many of the existing verification methods. So one method we discussed is using a randomization-based verification approach to achieve scalability. Basically, the story is you can use Gaussian smoothing for a badly behaved model to make its behavior better, make the loss landscape smoother. But the compromise is that you have to sample a lot of points during runtime to make sure to get a majority voting to get your prediction answer. And some people question that is randomized smoothing it's a valid verification technique or not, because you only get a probabilistic guarantee, like you don't have bad points in 99.99% probability. But for large scale vision models, that's probably the only way that works for among current techniques. And but for some real-time systems, this technique requires sampling. But people commented that if we can pack all the samples in one batch, we can run the sampling on GPUs, so it's still relatively efficient. And back to the GPUs and the scalability, people raised concerns on the verifiability of the GPU itself, because people have been designing CPUs for many years, and these CPUs, when they are designed, they were also certified to be working correctly. But for GPUs, because its applications was on graphics processing, the errors in GPUs is probably doesn't matter too much. But for us, if we want to use GPU for some critical applications like aircraft, then the verifiability of GPU itself, that we can guarantee that the GPU can always produce the correct answer, is actually also an issue that we need to deal with. And people mentioning like NVIDIA is currently trying to make their GPU more verifiable itself. And we hope the situation will change later. And people also mentioned that for those machine learning accelerators like GPUs, we typically have numerical approximation errors, because on those hardware the precision is typically lower, and some modern machine learning frameworks such as PyTorch and TensorFlow, you cannot manually control the rounding of your computation, because everything was done like in a black box manner. You don't have that low level control for that. So the numerical stability problem can also be a headache for using these machine learning accelerators. And my comments on that is we can definitely use GPUs to accelerate our verification process. And if we have some data points that is maybe near the boundary or something, and we are not sure if it is beyond the capability of the precision of GPUs, we can always double check these points on CPUs and with more accurate floating points. And what we also discussed a little bit about the benefits of having like machine learning models in like critical applications in like aircraft, and how much can we gain from AI. And because we have to pay a cost to verify the system to make sure it works correctly, and it usually can be really hard, especially if we have some computer vision inputs. I think one very good comment made by Melanie is that there are situations where even we don't have like verifiability for even we can't verify those systems. This system can still be valuable. For example, if suppose a pilot on an aircraft has something wrong happened to the pilot, and the aircraft is going to be out of control, and in that scenario, even if we have some machine learning models that can control the aircraft, even if it is cannot guaranteed to be 100% perfect, it can save our life. So it's still a valuable approach. And lastly, we discussed a little bit about the perturbations we need to consider in real-world verification problems, and especially as Vahid mentioned earlier, we need to consider physical-based perturbations. Like we need to try all the possible image that has a road bent to the left, for example, and it's really hard to enumerate all the possible images. And we discussed about using generative models, trying to generate a large amount of images that satisfies our needs. But the issue is currently the generative models themselves have some issues. So we cannot guarantee that we can generate all the possible image. But I guess that is still a good approach to at least augment our data set to make sure we have sufficient test data for testing the behavior of our system. So that is our discussion.
So we touched both the scalability issue and the complementarity issue. So for the scalability, we first start with an projection of when we think existing methods can be applied to real world problems. And the guy provided an estimation that in 2 or 3 years, we'll see an order of magnitude 2 orders of magnitude faster algorithms. And we can apply those algorithms to policy neural networks, because in general, I would believe there are more interesting applications and more important applications that is tangible compared to currently a lot of image-based classification networks. And Guy also pointed out we do see a lot of improvements of the scalability over the past years on the formal methods. And the second point is that we believe abstraction is a very good step for the scalability. And Guy's previous talk is on the abstraction on after a network's trained, and the only abstract in the verification step. And we believe that abstraction throughout the whole learning and the verification step are all very good to encourage the scalability. But we need to find good ways to do this abstraction in the training phase. And then the third point is that we believe we need a better understanding about the performance boundaries of existing methods. And the last point is that we did observe that in some literature that people on the formal methods, people are not actually addressing the real problem. For example, they tackle the robustness problem for image classification networks, but only try to find the perturbation bound for one image, which is not the actual real problems that we need to solve. So maybe in order for the whole research area to advance, maybe we can think about more on tackling real world problems, especially those associated with those perception networks. Okay, and then for the complementarity, we actually consider this problem in 2 aspects. So first aspect is how can we compose different techniques together? And some of the points are already covered by the scalability part of discussion. So for example, in the SMT solvers and in Marabou, they're already composing different algorithms to perform the deductive steps and bound tightening. And we see very promising result there. And also in some of the real applications, people combine control analysis with those neural network verification to analyze time series data. And second complementarity we're talking about is how can we bring different communities together? For example, formal methods people, adversarial training people, machine learning people, and maybe some control people, or robotics people that face the real world challenges. And that one way of bringing those people together is that we can create a common framework or common language for those people, and to ensure that we can understand each other. And based on this understanding, we can develop more fruitful collaborations and maybe compose of different methods together from different community, and also apply some of the methods in one community to solving the problem in another community. And more concretely, we think maybe a good way to do that is to create a benchmark problem, which needs the participation of our community to solve. And maybe in the future, we can organize some kind of competition to solve those kind of benchmark problems. And for the competition, we will try to encourage groups, encourage people to form groups of mixed expertise, so then they can learn from each other.
Maybe just a remark on the last element on competition with mixed teams. You can also think of hackathons, where you build teams to solve, which I think would be a bit more, well, you can do that in a competitive way, but yeah, that could be, I think it's a good idea to, we need to find the right use case and stuff like that, but that could be really a nice way to foster these exchanges between communities and trying to find new solutions, maybe by mixing skills. That's a really good idea, I think.
Great. Thanks, Jeannette. I would like to add also one comment regarding the data collection. So there are already some available data sets that have been used by the machine learning communities and nowadays by the verification community, like Kitty data set. That is quite well known for verification and also validation of the neural networks. But on the other side, there are also some companies like our company Audi that have have published a data set that have been collected from the realistic scenarios. For instance, we have collected data from Ingolstadt, from Munich, and if I'm not making a mistake, in Nuremberg. And all these data are public now for all research in both communities in order to basically work towards the improvement of the algorithms. But in general, we may also face some problems in order to share the collected data, as we already faced with one company beforehand with respect to the legal issues, GDPR. So basically, if you collect some realistic data, then you need to also handle all these issues in order to publish or to make for all scientists. That's a big issue, I would say. Unfortunately, in such Volkswagen Group, we have not found any solutions to bypass. As I said, there are already some data sets, even from the realistic, can be definitely used for even for the competitions or like hackathons that Jan was discussing about. Other questions?
I have a comments on the dataset part. So I think I think it is like crucial to have some standard benchmarks for verification, and so far like in many papers people focus on some toy problems like MNIST and the CFR10. That is not really good, but for studying a problem is good, but we look forward to seeing like more and more data sets from industry, from the real scenarios, data connected from real scenarios. That would be actually better to convince people that our technique is more is valuable. Because if I just talk about MNIST and CFR10 for some people who do not understand the verification problems, and they will think, oh, this doesn't really quite make sense. It's not really useful. But if we can show some like the aircraft control, some maybe some data sets from Audi, then they will see, oh, there's some real usage of this verification techniques, and it can help us to build a better machine learning model.
So actually, I have a question for the point raised by Huan earlier in his summary. I think it's a very good idea to use a generative model to generate images to verify like image classification networks. Have you thought about but if you want to generate those images and then start verification from those generated images, you're still facing the problem that you cannot account for the infinite cardinality of the image space that you're still doing finite approximation. Have you considered to do your verification like starting from the seed that you put to the generative model, so that you don't need to do the sampling? Yeah.
Yeah. I am not sure if someone has done that, but I think yes. So for example, if we suppose we are using GANs, when we start from maybe some random noise or something, starting from a seed, like you said, and we generate some image, we can definitely verify the whole system end to end. So we take the seed as the input of the entire system, and the seed is the input for the generative model, and the generative model outputs some image, and the image is the input for the classifier. And if we treat the entire system as a whole, then the input is just the seed. So we just want to make sure like for all possible seeds, the verification, the output won't change. For example, we can suppose we usually add a small Gaussian noise for the seeds. We can for example, we can guarantee that for see the seed as some input perturbation. So for example, if the perturbation is L2 norm is less than 1 or something like that, so then we can capture the majority of the Gaussian noise, and the output of the system can be verified as a whole. But of course, the limitation is that we have to guarantee that the generative model indeed produces very good image for all the possible states. If the generative model just produce a single image, then even if it can be verified, it doesn't make too much sense. So yeah.
Cool, great.
Yeah, I'm not
if
sure.
I may, I think it's a great idea, and I would encourage you to work on this.
Yeah, I'm not sure if anyone has worked on that. Maybe, but I'm not aware of any end-to-end verification based on that. Yeah.
So actually, one of my students thought about this issue earlier on and told me that may be a promising direction. But later we find, even though we can guarantee the generator is correct, the current formal verification approach may not work very well, because even your input is small, output may be also small, but the width of your network is very big. So the current reachability-based method can still blow up when you propagate to the middle.
Yeah, I think the usual approach to scale up, we didn't mention that in earlier discussion, is to actually train your models with those verification techniques. Like for example, using the linear relaxation-based verification technique, these methods are relatively cheap. So you can actually, during training, you can consider this kind of bounds to make the bounds tighter. And that's currently the only way to scale up. Like for me, I try to train ImageNet, a very large data set, using those verification algorithms. So basically, I train the network such that the bounds becomes tight, and so such that after training, I obtain a network that the bounds are tight and the classification outputs are correct. So if you don't use training, I think it's gonna be quite difficult to give some verification guarantee for these big networks. But if you do training, I think that can partially solve the issue. Yeah.
Oh, that's great to know. Yeah, maybe we can discuss more this offline and maybe start a new direction of research.
Yeah, definitely. Cool. Yeah.
Mm-hmm. Yeah, maybe let me try to understand the question better. So are you asking that if we can add the specification, like probably embed the specification in the structure of the network, so that in the real execution, even though there's a change of distribution of the data, we can still have some formal guarantee? Yeah, in that case, I think if we were just dealing with like control networks, policy networks, that there's ways to deal with that, because usually a control specification can be well obtained through your system analysis. If you want your system to converge at a certain rate, then you just use a Lyapunov analysis, decompose that system level specification into a controller specification. And usually those control specifications is very simple. Usually what we are encountering in real practice is just a half space constraint, which depends on your input. And it does not matter whether your input is out of distribution or not. And then we can add that constraint directly to the last layer of the network, kind of a projection of the network output, so that no matter what data comes in, it will automatically guarantee the satisfaction. Yeah, there's a method called shield NN, shield neural network. Yeah, they just directly add those projection, half space projection to the last layer. And I think there are more work going on, and we are also studying that, because we can do the shielding after we finish the training of a network, or we can directly add the shielding to the network that's doing the training, so that the network knows that there's a projection layer after the nominal output.
Yeah, for me, I think that's a very hard problem. I don't know if there's any straightforward answer. And I know, yeah, that's a real problem we need to solve. Like for real test of a product, we have so many factors. For example, you have a lighting condition, you have maybe weather condition, you have so many variables, and you can change and combine them, and we will have like so many combinations. And I'm not sure like how to efficiently look for the worst case among all of them. I guess one approach is probably I'm not sure, just some random ideas. Yeah.
It would be all fine if you brainstorm on that. We are looking for brainstorming here.
Yeah, for example, I can train a generative model like a VAE or whatever. I can make the generative model generate. For example, my generative model have 10 inputs, and each input is controlling one of the condition. For example, one input is conditioning on the lighting condition, and another input is conditioning on maybe on the color of the background. For example, whatever. Suppose we have 10 kinds of inputs, and our generative model can suppose it's something like a GAN or VAE, and if it is differentiable, then we can actually differentiate through this generative model and find the worst case combination of the 10 inputs. For example, we can run some gradient ascent or something to maximize the error and to find the worst case combination, at least approximately worst case combination of the 10 input conditions. That is my thought. But of course, this won't cover all the situations, because you have the generative models. If the generative model is not good, then you cannot have any conclusion. But suppose we have some good generative model that can control some factors of the generative image, then we can suppose the generative model is also differentiable, and we can actually use gradient descent to find the worst case scenario. That is used for testing for ensure safety.
Yeah, I think the approach Huan mentioned is very interesting. That is also something that we're currently trying to do. But we are doing that for a different application. That is how we can validate that our learned human model can capture the human behaviors in different human-robot collaboration situations. And it's very difficult to cover all the test cases. And currently what we are trying to do is to do adaptive domain randomization, kind of a way to do adversarial search, to search for the hard human behaviors that may not be perfectly detected or predicted by our model, and then let the human do that behavior to see if our model is correct or not, and to keep doing that. Yeah, so for now, we don't have a very good approach. So for now, it's just if the prediction is out of our common sense, then so for example, we know that humans' behavior will not exceed, or humans' joint acceleration will not exceed certain limit. Then we try to find is there an input that lies in our predefined input distribution, but maps to a point that the joint acceleration in the future steps will exceed the limit. If it is the case, then we find those input trajectory, let the human do one of those mimic those kind of trajectory, and let the robot do the detection. So that's a very early phase that we're trying to work on, but there's definitely a lot of problems to solve on the way.
To add 2 points. One, going back to modifying neural networks for in some sense, adding constraints for provable guarantees. There's also some work that I'm familiar with respect to provable robustness guarantees that's inspired by differential privacy. And the idea is to deliberately add a layer of noise into the neural network that will give you a provable robustness guarantee for instance, input images. And so this is an interesting approach, because it's constructing the neural network by construction to be correct with respect to robustness guarantee. And the second piece of work I wanted to just allude to is in terms of testing, obviously, rather than test one behavior one at a time or one test case one at a time, the testing community has also used symbolic testing as a way to represent for, symbolic test cases to represent multiple test cases. And some of the work in interval analysis might be relevant there for a space that is, as Changliu said, infinite cardinality.
So it's not directly related to what you said before. It's just that this year and last year also with other colleagues, we try to push to NeurIPS some workshop on just like this, on formal methods and empirical robustness to promote this kind of activities to the NeurIPS community. And we received good feedbacks on the construction of the workshop, but the committee thought that it was not a subject important, relevant enough to the community. And I think in this panel, we all think that this is not true. So do you have any idea on promoting and raising this topic to the wider machine learning community? The problem is that the workshop was not accepted in its life. It's more that you have more impact being in the academic field to spread the word and to promote this topic, which are really of high importance for the industry. So please help us to promote these kind of activities.
Yeah, I think one point I want to add is that it's really important to show some important real-world applications of those verification techniques. So people are not aware of those who are using these techniques. Like in my experience, like for example, the field of adversarial robustness is popular in machine learning. That is because there are some people demonstrating like adversarial examples exist in real world. Like before that, the adversarial examples was discovered many years ago, but the people didn't pay too much attention because people think that's just like some because the noise is don't really happen in practice. So those are just some toy problems. Maybe just the problem just it's not realistic. So there's no realistic scenario you can find adversarial examples. But after people finding some real world like physical adversarial attacks, so this field becomes like more recognized, and people thinking like this is a more important topic to study. So that's why I think some real world application can be helpful here to promote this field.
Yes, thank you. Vahid, regarding what you said a bit earlier, and perhaps also directed to everyone else, you mentioned the GDPR, and I wanted to make sure that I understood it well, as sort of a hurdle in practice and a hurdle in using real world data. I wanted just to make sure to what extent it is perceived like that and experienced like that. And if this means that as an alternative to that, you use non-real data, or I don't know how to call it then, and to what extent that data would be relevant when we're talking about generalizable robustness. Okay, because currently it's not very delineated yet, but there is something as a research exception principle. And this is also subject to a lot of safeguards and so on that you have to do, such as anonymization and pseudonymization. But indeed, but my question was also to what extent is this artificial data set then still relevant when we're talking about robustness? Because that's also the other end of the spectrum, is that we also need this reliability.
I would like to thank all the panelists and you, Vahid, for moderating this. It was a very rich and dense session. Thank you very much. There are lots of ideas and that really came from the discussions. I hope you find this as interesting as I did. So thanks a lot, really, for that.
I would like to also thank the panelists from my side for plausible discussion. I learned a lot, and there are definitely a lot of things that we can do together. In the future, at least we understood that we have a lot of challenges to solve for safety critical systems, and that would be actually a very good starting point to move towards a better future. Thanks a lot to all the panelists.
Thank you.
Thank you very much. That was great.